necessary questions that you have. So the second FTC in general informs us how we take the derivative of these integral defined functions. Why might we be able to take the derivative? Finding the tangent line would be one of those examples. So did remind us of kind of this top left-hand corner, the general formula again that we always use for a tangent line, y minus y1 is equal to m times x minus x1. And so then if I'm trying to find the values on that, we know that y1 is going to be basically the y value of the original function. That's going to be f of pi over 6. M is the slope, which is going to come from f prime. And then, of course, x1 is the value that we're finding the tangent at. I like finding my coordinate first. So I'm going to plug pi over 6 into the original function. By plugging it into the original function, we're replacing every time we see an x with pi over 6. That in turn just becomes a regular definite integral. How do we find a regular definite integral? We need to find the antiderivative. That 1/3 showed up from u substitution. If u was 3t, then u prime would be 3. The antiderivative cosine is sine, and then plugging in the top minus the bottom gave us this value of negative 1/3. So that is the value of the integral, and the integral is the y value of f. So if I'm trying the tangent line, y minus negative 1/3, that's where that plus 1/3 came from. And then to find the derivative, we need to find f prime of x first. And so this is where the second FTC comes from. And the second FTC, we know we have the general case and the common case. For this one, we would have to use the general case because your bottom is not just an x and your top, or excuse me, your bottom is not just a number and your top is not just an x. Yes, Taylor?
Why isn't it negative sign? Because isn't
the derivative of cosine is negative sign, but the integral of cosine is positive sign.
Oh.
Because the derivative sign would be positive cosine. So finding f prime, again, that's going to be the second FTC. So remember, the second FTC, you plug in the top times the derivative of what you plugged in, minus plugging in the bottom times the derivative of what you plugged in. So that would be the expression f prime of x. F prime can be used to find the slope. I want to find the slope at pi over 6. Plugging in pi over 6 in for x, and then evaluating that trig, you get the derivative is negative 2. And so then the slope would be that negative 2. This question could have very well been like a calculator question. It probably would have made it a whole lot easier. If you could have done that whole first step of the f of pi over 6 in the calculator, still would have had to find the derivative by hand because that would require knowledge of the second FTC. But then you could use your calculator to evaluate it. But just mispractice it with no calculator, just also to review how we find antiderivatives. Questions on that problem? All right, so moving on to the second question. This is one, again, guaranteed you're going to have a question like this tomorrow. Where you have some function, and then you also have another function that's going to be defined as the integral of the one that you have graphed. Several ways to kind of think about this one, but always pay attention to, especially for that integral, what number is on the bottom. This integral, if we have to find its area, is going to start at 5. Again, that could change from function to function. And then I like writing down the relationships first. So like if g of x is the integral from 5 to x, by the second FTC, the derivative of g prime is just going to be f of x. We're replacing the t with the x. And if g prime is f of x, then g double prime is going to be f prime. I had a similar question to this on the quiz, and I have another similar question like this on your test. It asks you to find g of 3, g prime of 3, and then g double prime of 3. G of 3 just tells you to replace the x with a 3, so that becomes the integral from 5 to 3. I will say I wrote this problem before actually working it out, and I honestly didn't mean for it to land at such an ugly kind of y value of that 1.5 right there. On your test, I am not going to make it that ugly of a number, to be completely honest. I will make sure it lands on a whole number. But we are having to find the area, so if I wanted to find g of 3, that's the integral from 5 to 3. let's talk about this area. If we're starting at 5 and moving backwards to 3, this area is above the x-axis, but we're going backwards. So what would be the sign of that interval? Negative. So we know it will be negative no matter what. And then I just need to find the area of the shape. So I kind of thought about it as I had a rectangle. So we had base times height. I had that tiny triangle, 1/2 base times its height. And then I had that larger triangle, 1/2 base times its height. I could simplify it, but as long as I know it's negative, I can leave my answer honestly like that. Again, for your test, I wouldn't make you have an awkward 1.5 there. I would make sure it lands on a better y value. Looking at g prime of 3 will be the same thing as f of 3. That's just the value. Well, what is f of 3? 1.5. And then for that last one, g double prime of 3 will be the same thing as f prime of 3. F prime is a derivative. How do we represent a derivative with a slope? What is the slope of this line? Up to over 4. 2/4 is fine, or of course you could reduce that as 1/2. Very important though that you kind of recognize and remember how to do this relationship when doing those problems. Questions on that one? All right, then looking at B. B asks us to find the zeros of G. So another word for zeros we know is like the x-intercepts. So this question is basically asking us to find when g of x is equal to 0. We don't know what g of x is, but we know what g of x is equal to. What is g of x equal to? It's equal to that integral from 5 to x of f of t dt. So basically what we're looking for, the zeros of g is when that integral would be equal to 0. Without even scrolling back up to look at the graph, there is one easy x value to find. What easy x value is going to give us an integral that's equal to 0? 5. You start at 5 and end at 5. You have no area, so you know that it would be equal to 0 there. The interval would be equal to 0 there. Do you want to go back to the graph to see if there's any other locations? There could be. This one, there's not. So again, if we're starting at 5, if I move forwards, looking at that area, it's all negative. There's not going to be a chance for that to become like negative and then positive and cancel out. Also moving backwards, it's all above the x-axis. So there's not going to be a chance for that to be like negative and then positive and then cancel it out. So there's never going to be a time where that integral is going to be equal to 0 again for this example. So x equals 5 would be the only 0 we have in the graph for that question. Questions on B? All right, and I'm going to go ahead and do C and D kind of together because they are treated similarly. Many of you are actually good at this type of question on the quiz. Some of you got the answer. What was wrong was just kind of how you justified your answer. So if it says when is G increasing, think about what that means in calculus. G would be increasing when G prime is positive. Or you could say greater than 0. That would also be perfectly fine. But we don't have the graph of G prime in front of us. What we have in front of us is the graph of f. Well, what is G prime equal to? G prime is equal to f, and you would want to state that. So if I'm looking for when G prime is positive, we're basically looking for when f is positive. Well, in what interval is the graph of f positive? 0 to 5. And then D is going to be similar, and I'll take kind of questions on C and D. It says at what x-coordinate, if any, does the graph of G have an inflection point? I don't think we've done inflection points in a while, so good time just to review those in general. When we talk about an inflection point, that is where concavity changes. So basically where the function would go from concave down to concave up, or vice versa, concave up to concave down. Typically, we look at that as when the second derivative changes signs. But we can also identify a point of inflection where G prime changes direction. And when I say changes direction, basically where G prime would change from like increasing to decreasing. So if I'm forming my answer for this one, we're going to have to use that third option because we only have the graph of f in front of us. So again, I'm going to do my reason first because G prime, which is equal to f, changes direction. And then at what x value, if any, do we see a point of inflection for G?
4.
At 4. So again, that is the maximum of f, but again, we're talking about G, and that would be a point of inflection of G. And again, how we're interpreting that, you can kind of look at it as the function of f has like a positive slope and a negative slope. So it's like the second derivative of G is going from positive to negative. And then I put E on here. I think we did a lot of time this unit doing absolute extrema, so I did just want to take a time just to review relative extrema. If we have a relative minimum, the derivative would need to change from what to what? Negative, positive. So minimum, you go down first and then up, so it would change from negative to positive. So G would have a relative minimum if G prime, which is equal to F, changes from negative to positive. Is there a time where G prime, which is equal to F, is changing from negative to positive?
5.
So it does, something does change at 5, but what is it changing to from 5? Positive to negative. So does this graph have a relative minimum? No. So I'm just going to say there's like none. Why? Because G prime, which is equal to F, never changes signs from negative to positive. What is happening at 5? That would be a relative maximum because it's changing from positive to negative. G prime, not for me not to use it, G prime, which is equal to F, is changing from positive to negative. Any questions on those last three? Yes, Mitch?
So would the inflection point for a graph of f be x equals 5? Because it's from...
The graph of f, if you're just looking at f, there is no point of inflection point because there's no concavity in that graph. It's just a bunch of straight lines.
Okay.
But typically for these problems, if people like memorizing this way, if you have like g, which is an integral of f, g, the one that is defined by the integral, will have a point of inflection at maximums and minimums on the graph that you can see.
Oh, okay.
Any other questions or things I can clarify on that? All right, so I'm just gonna go ahead and let y'all get started. Again, I'm here to answer questions all period long. Some things I did just want to kind of remind you of. So you have your homework to work on. You have the briefcase binder. Looking at the view count of the video, some of you might need to be reminded that if you're stuck on the quiz or kind of working on those quiz corrections, remember I did record myself kind of explaining each question on the quiz. You're welcome. To find that link, it is in the answer key folder. There are 2 old tests. Some people told me I guess they were super eager, which is great that they already worked out the practice test in the answer key folder. So I went ahead and uploaded my BC test from this year so you can have a second one to practice. It might be more of a fun test to take because it is Toy Story themed, but it is in there for you to practice if you want to. Probably heard it from other teachers, but this is kind of like in the future. Towards the end of March, we know the high schools will have virtual days on the 25th and the 26th, and we'll be on the URL schedule those days, and then also the week after spring break. Last thing I wanted to say is definitely ask me all of your questions between now and the end of class. If you would rather ask questions in like a smaller group setting, or maybe you're just working on stuff after school, like if you're here in person, then clearly just stay behind and ask questions after class. But if you're at home and have some questions you want to ask in a smaller group setting, then in Teams, there is a link to a meeting that basically all my AD students have access to, and you can ask me questions after school in that meeting. And I'll have it running to 4:15, but honestly, there's not a lot of people in it, and it hits around 4, then I'm probably going to go ahead and close it out. But y'all can go ahead and get started. I'm here to answer